Thank you. Is it on? Yeah. Okay, let me start by picking this. Let me start by thanking the organizers for having me and for putting the event together. I will talk about two-point functions at finite temperature in holographic conformal field theories. And this is based on two papers with two great collaborators, Ivan Gusev and Andrei Parnachev. Good. So let me start with some general motivation why to study conformal field theory at finite temperature. And there are various reasons, starting from experimental ones, that quantum critical points in laboratory are always measured at finite temperature. But there are also plenty of good theoretical reasons. And they are starting to be more and more explored. And one of very interesting directions, I think, is that high temperature correlation functions control heavy sectors of CFT. So density of states at large delta and also P coefficients. And this generalizes formulas such as Carty's formula for density of states to higher dimensions. There are also some ideas how to formulate numerical bootstrap with thermal correlators, and these I think are also very interesting. And all this is part of maybe a general program of studying CFTs at different geometries, and then trying to formulate some crossing symmetry constraints involving correlators on various geometries. When the theory is holographic, then there is also a little bit different flavor, because these thermal correlation functions should be related to black holes somehow. And in this talk, this will indeed be the main topic, how thermal two-point functions are related to fields on certain black holes. Okay, so let me describe the setup and formulate the problem that I want to solve. So among various thermal geometries, we'll look at the most standard one, where I have the thermal circle times the flat space, and beta is the inverse temperature, and we'll stick to 4 dimensions in this talk. And the observable that we focus on is the two-point function of a scalar operator, G beta. And I will also, to make things simple, put the two scalars at the same spatial point, so they will only differ in their Euclidean time coordinate. And then this two-point function only depends on a single variable. And it is an interesting correlator because it satisfies two properties. One is the conformal block decomposition, which in this configuration is very simple. It's just the decomposition in powers of tau. And these coefficients, A, are called the thermal coefficients, and they are the dynamical coefficients that characterize this two-point function. On the other hand, as in any quantum field theory at finite temperature, this is periodic in Euclidean time. So this is called the Kuba-Martin-Schwinger condition, KMS. And now you see that blocks individually are not periodic. So imposing this periodicity on the correlator gives you some rules on the thermal coefficients. And this logic sometimes goes under the name of thermal bootstrap and has been explored with good success in these works by Ilija et al. And Marquette et al. And mostly in the context of Ising and ON models in 3D. And there is pretty good agreement between these bootstrap results for thermal coefficients and, for example, Monte Carlo results. Today I want to look at a different type of theory. So I want to look at a holographic CFT. And let's say an operational definition for this talk of what I mean by holographic is the following. So I'll look at the two-point function of some scalar, which you should think about as a single trace operator. And then I postulate that the OP contains 3 types of operators: the identity, then a tower of double trace operators, and what I will call multi-stress tensor. So these are composites of the stress tensor. And the scaling dimensions, and you can argue that indeed in large N gauge theories, conformal gauge theories, these are the only contributions at leading order. And the scaling dimensions at leading order of double traces are 2 delta phi plus 2m, and of stress tensors are of the form 4n. And then there are 1 over n corrections, but in this talk I will just assume that these are exact. It turns out that the thermal coefficients for the stress tensor sector, so the stress tensor and all the composites, are very well understood, and I will review this from the work of Fitzpatrick and Huang. And the aim of today is then to determine the thermal coefficients of these double trace operators and thereby determine the whole two-point function. Okay, so this is the plan. I will first review this analysis of the stress tensor sector, which proceeds by solving some differential equation in the bulk. Then I will describe how these KMS sum rules can be used to, from the stress tensor coefficients, determine double trace coefficients. And then I will show some results of this procedure and conclude with some future directions. Of course, interrupt me if you have any questions. About the stress tensor, so how are these coefficients computed? One looks at the Klein-Gordon equation in the planar ADS-Schwarzschild background. So this is the metric where mu is related to the temperature. And then if you write the Klein-Gordon equation on this background, these authors noticed that if you make the ansatz of this form, this is closed under the action of the Laplacian. So these rho, r, and w are some new coordinates. And what is important is that rho going to infinity is the boundary. So this is kind of a near boundary expansion. But this function shouldn't be thought of as the full two-point function when you push it to the boundary, but only the stress tensor part of the two-point function. And indeed, if you expand this ansatz, if you take this ansatz and push it to the boundary, you will only find stress tensor blocks in the corresponding two-point function. So you can compute these coefficients ijk by acting with a Laplace operator. This gives you some equations for these coefficients. And they can be computed to pretty high order. For purposes of this talk, I should say that we needed to extend this to rewrite this as some kind of recursion relations, which are familiar from Casimir equations in conformal field theory, but it's a technical point. Okay, so you can actually go beyond this. So the problem with this ansatz is somehow that it doesn't take into account conditions at the horizon. So you can numerically try to solve the Laplace equation where you impose both sets of boundary conditions, and this was done actually in the paper by Parisini, Skenderis, Withers. But it's a very difficult numerical problem. It's a partial differential equation in 3 variables, and the precision that you can achieve is not great. So using this method, you can determine the first, well, they determine the first double trace thermal coefficient, and maybe you can push it to the second or the third, but let's say if I want a 10th double trace coefficient, there is no hope using these numerics to determine. Okay, so we will approach this problem by field theory methods, but let me also, before going there, just mention that if you analyze these coefficients of the stress tensor sector, I will call them lambda n, if you just compute a lot of them and see how they behave for large n, then they have this exponential growth, -4 to the n, and then some power. And if you sum this up with conformal blocks, you will find out singularities in the complex tau plane. And these are called the bouncing singularities by some analogy with bouncing geodesics in the bulk. But what is important in the full correlator, so in the full two-point function, these singularities should not be there based on some very generic quantum field theory arguments. So somehow these double traces are also needed to cure these singularities in the full two-point function. Okay. So let me then describe the method and the results. So in order to write down a system of sum rules starting from the KMS, for example, you can take derivatives at the crossing symmetric point. Odd derivatives should be 0. So each of these, for each k here, you get a linear equation. So this gives you an infinite system of linear equations which involve the thermal coefficients. And I have separated them. So this is specifically in the case that I have this holographic spectrum. I have separated them so that I view this system as a system for double traces where I know the lambda ends. I should say in this form, these equations were written in this paper. And okay, I will, for convenience, just rescale the double trace coefficients in some way. So now you can look at this infinite system of equations and look at its structural properties. And in particular, there are two interesting observations. The matrix, when you write it in a matrix form, is upper triangular, which means that you can solve it efficiently, the system, by backtrick substitution. But it's also a Toeplitz matrix, which means that it's sort of self-similar. If I start looking from here, it looks the same as the full thing. So if I solve for the first coefficient, A1, then I have solved for all other coefficients. I just need to shift some index. So this is, in any case, if you go through this procedure, this is a formal solution. AM is an infinite sum. And these Fs are just what was on the right-hand side. So they are combinations of these gamma functions and then the stress tensor coefficients. So indeed, you see this M only shifts these Fs here. So this is a formal solution because it's an infinite sum, and you should worry whether it's convergent. And in fact, even for the generalized free field, this sum is actually not convergent. So you need to resum it somehow, and I won't go into the details, but what you should do is Borel resum this. So you essentially take this expression, and the Borel resummation is captured by these steps. I'm dividing by 2k factorial. I have some Borel variable, and then I'm taking the inverse Borel transform. So this is the formula that we propose should be used, and I will be somehow using this formula for the rest of the talk. So let's do some checks. First of all, if I apply this formula to the generalized free field, it recovers the correct double trace coefficients, which were known before. A more interesting statement is that if I take, this asymptotic behavior, if I for a moment pretend that stress tensor coefficients are exactly given by this asymptotic formula, then I can perform this sum exactly again and compute the two-point function. And the two-point function, if I look at it in the complex tau plane, satisfies, well, it's KMS invariant with this spectrum, but it's actually free of singularities in this strip from 0 to beta. So this, and then it's extended by periodicity to the rest of the complex plane. So somehow this Borel resummation magically kills off the singularity. And it's also bounded as you go to imaginary time, which is also a necessary condition for thermal two-point functions. And actually, if I take these three properties, they seem to be defining a unique function. So we didn't really try to prove this, but it seems to be true. So it's somehow interesting that this seemingly unique function is indeed recovered by this solution, Borel resummed solution. Okay, so now we want to go a step further and go beyond this asymptotic regime, thanks, and input the exact stress tensor coefficients. So we don't have infinitely many of them. We can only compute finitely many of them, so we need to use also some numerics. And I won't go into the details, but essentially that means that you need to do both Borel resummation, which is slightly different from the one that I showed, and some Padea approximation of the Borel variable. So you the Borel, then you do Padé, and then you invert. And this gives you an approximation for the double trace coefficient. And what controls this approximation is this capital N, how many stress tensors I kept. So what I want to do is increase this capital N and see if this procedure converges and what are the numbers. So this is the picture for some examples of double trace coefficients. So you see this converges pretty well. For the first 8 operators, this table shows the result, and the number of digits that is kept here is the number of stable digits under increasing n further. So I should say this n is around 300 for this example. This is how many stress tensor coefficients we can compute. Another check of the resulting two-point function is this behavior along the imaginary tau direction, that it should be bounded by the value on the real axis, and this is also satisfied. Finally, you can try to compare. I said that the partial differential equation in the bulk is not really possible to solve it very precisely, but you can kind of solve it and then substitute these Padé-Borel values for all the thermal coefficient except for one. And then this gives you an estimate for let's say I pick this coefficient. This gives me, as this black estimate is kind of what I get from the partial differential equation if I substitute for all the other double traces. And you see, and the green one is the actual Padé-Borel for the same coefficient. So here there are comparisons of these numbers. So you see that these numbers are always fairly close. And here I just put the GFF, generalized free field, to show that they're both well separated from the generalized free field, so that it's somehow not every two-point function looks the same. In this case, also this asymptotic model works pretty well, but that does depend. So this is for external dimension 3/2. This depends a little bit on the external dimension. So we have similar results for 5/2. Okay, so let me summarize. We proposed this method, which is essentially just based on simple linear algebra, how to solve KMS conditions, KMS sum rules, but it does importantly require this resummation in order to converge. We applied it to these holographic CFTs to learn about the double trace data and in turn the full two-point function. And it passes several consistency checks. There are some obvious generalizations, like you can repeat this where the points are separated also in space. I think this should be relatively easily done, and then you would be probing thermal coefficients distinguished by spin. Or you can go to finite S1 times SD minus 1. Then you are really probing the actual OP coefficients of the flat space theory, so this is also very interesting. In even dimensions, probably this can be carried out in a very similar way because the stress tensor sector is known in all even dimensions, or the method to compute these coefficients is known. There are other interesting directions, like from this knowledge we can now start looking into the result, into this two-point function that we got and its properties, compute maybe Lanczos coefficients, quasi-normal modes. Importantly, I think also some of this is very general. You don't really need to have a holographic CFT. Well, KMS condition is of course true in every CFT. It's a question where you have this separation between different towers of operators such that one fixes the other. So this is an interesting question, I think. And a model that we are looking into is large N1 model, which has sort of a similar structure. Finally, it would be also very interesting to go beyond large N, or to have some field theoretic computation of these thermal coefficients, which I'm not familiar with any such calculations, but yes, it would definitely be interesting to have those. Thank you. Well, we have time for a couple of questions.
Why do you have only phi and TT in the OPE? Why there is no phi TT? Well, phi T.
They are suppressed at large N.
Phi T?
Phi T, yes, yes.
Why would they be suppressed?
By powers of 1 over n. I don't know exactly by what powers, but they are suppressed.
So what would be the action you consider? I mean, gravity action.
So no, we don't. I mean, it's just the counting of powers like this. You can think of this thermal 2-point function as a 4-point function of 2 heavy operators and 2 light operators. And then if you write diagrams, so let's say I have these 4 operators now, 2 of which are light, 2 of which are heavy. And then you have graviton exchanges or you have scalar exchanges. And then if you have more than a single graviton, for example, if you have graviton loops, you can do, when you do the counting, they all contribute at the same order. So this is why you have these multi-stress tensors. But I mean, I don't know. We can do the counting after. I don't think it's very, very deep, the statement.
But when you do the computation, you just use the gravity background, right? The black hole. Well, it's thermal ADS-CFT background, ADS background. So in this background, what action for the scalar field would you consider?
In this this is just minimally coupled scalar. Yes, yes, yes.
Just free action, or not?
Yeah, this is just free. And this will depend. Of course, you can do a different coupling, and then the stress tensor sector will change, and then the double chase sector will correspondingly change.
Well, thank you, Ilija, for the talk. Yeah, I was interested in the large N1 model, like what are the...
Yeah, so the structure looks similar because there, when you introduce the Hubbard-Stratonovich field, then you have double traces made of phi, and then you have the powers of the sigma field. So you have kind of 2 towers, and it looks then on a technical level very similar to what I was describing here.
Yeah, thanks for a nice talk. For the generalization, for example, finite separation, do you expect to have the same upper triangular Toeplitz matrix form that allowed you to have this nice solution? Or do you have any idea?
It's a good question. Actually, we are now solving it in a slightly different way, so we might. Yeah, I don't know. I think we have now a slight reformulation that works at finite distance as well. So maybe we will, do it in a slightly different way.
Thanks.